The spread of data is a measure of how far values are likely to fall from the center. This is a little bit different from range. For a normal distribution, the range is infinite, but the spread is determined by a parameter called the standard deviation. This picture shows two distributions with the same mean but different standard deviations, and I hope that it illustrates what I mean by spread. The standard deviation is the square root of another parameter called the variance. For a sample, we'll always write the variance as s squared, and the standard deviation is the positive square root of that, s. Now, the variance is essentially the average squared distance from the mean. You see, the numerator here is taking the difference of each point from the mean and squaring it. If you add these all up and divide by n, you'd have the average squared distance. But I say it's roughly the average squared distance because we divide by n minus 1 instead of n. And the reason for doing that is beyond this course. You'll have to study mathematical statistics to find out why that is. Anyway, let me show you how to calculate this. We need to find the mean and subtract it from each point. Square that, sum them all up, then divide by n minus 1. So here we're given a sample of three numbers. First, we find the mean, which is 8. And then you can see I take 8, subtract it from each point, and square it, and divide by n minus 1. The result is 13, and that's the sample variance. The sample standard deviation is the square root of 13. Now, that was a lot of work for just three numbers, and it gets a lot more tedious when there are more. So we'll always use R to find these. In R, the commands are var and sd. To find the standard deviation of the previous set, you would enter sd c, remember this C notation, 5, 7, 12, two parentheses. You could also do square root of the variance of those numbers. The standard deviation is a measure of how far the points depart from the mean. But what if you're not using the mean to measure the center of your distribution? If you're using the median instead, there's a different measure of spread you should use. It's called the interquartile range. The interquartile range is defined as the 75th percentile minus the 25th percentile. There are a couple of different definitions of a percentile. The one our textbook uses says that the 25th percentile is the point in the data such that 25% of the data is less than it. So let's say you have 100 data points ranked in order. You start with x1, x2, on and on and on, up to x25, x26, on and on, up to x100. And these are all in the order of their values. Then the 26th point would be the 25th percentile because 25% of the data is less than it. And the 100th point would be the 99th percentile. Often the data doesn't break into percentiles cleanly, and you have to interpolate them somehow, kind of like when you find the median of an even set of numbers. There are several different ways of doing this, so just trust R. We'll never find percentiles by hand in this class. The IQR gives us the boundaries of a box plot. A box plot is a graph that's used to examine the center and spread of a distribution. The box itself begins at the 25th percentile and ends at the 75th percentile. So this distance is the IQR. The dark band inside the box is the median. The whiskers extend to all the data points that are within 1.5 times the IQR of the box. If any data falls beyond the whiskers, they are suspected of being outliers, which means that they are remarkably high or low values. Box plots are usually used to compare several different distributions. Here we have the distribution of barley yields plotted by location. We can see that the median yield for Crookston was about 120. The 75th percentile is only a little higher, maybe 125, but the 25th percentile is way down here at about 100. That means that 25% of the data goes from here to here, and then the next 25% of the data goes from here to here. That indicates left skew because there's a decent amount of data down there way under the median. Similarly, University Farm looks like it might be right skewed, but we can't see multimodality in these things, so we can't be sure from the box plot whether there's skew or something else is going on. The box plot is really about comparing the center and spread of different groups. Like we can see from this plot that Waseca had the highest mean and maximum, so they're getting the best yields. Duluth and University Farm have smaller boxes and whiskers, so they have less spread. The yields in those places are more tightly clustered around the medians. Box plots and histograms are for visualizing numerical data. When we have categorical data, the most commonly used plots are bar plots, and there are a few popular varieties. A bar plot is a visual representation of a table. Here we have a categorical variable that represents what branch of the military people are in. To draw a simple bar plot of it, tabulate the data, put the categories on the x-axis, and scale the heights of the bars according to the numbers in the table. If we have two categorical variables, we have a few options. One is the side-by-side plot. If I want to see a breakdown of sex by military membership, I can draw a plot like this. Instead of having the bars side by side, I can stack them. This makes it easier to compare the overall totals, but when you have a lot of variables, I think side by side is better for comparing each individual bar because they all begin at the bottom. In another version of the stacked bar plot, we use proportions instead of counts. When you have a table like this, you can get proportions two different ways, using columns as the margin or rows. When the margin is columns, the columns all sum to 1. Here, we're looking at the proportions of males and females in each branch. The columns sum to 1, so I'm finding that the Air Force is 19% women and 81% men. The Army is 13% women, 87% men, etc. If the margin is the row, then the rows sum to 1. In this example, that gives us the proportion of military branch membership by sex. Among females in our data, 32% belong to the Air Force, 37% belong to the Army, 6% belong to the Marines, and 25% belong to the Navy. If you add these all up, they sum to 1. When you make these things in R, you need to pay attention to how it builds the tables and plots them. I'll cover this in the coding lecture. The book only shows one pie chart, and that's because they tend to be frowned upon by statisticians. A pie chart displays the same information as a bar plot, but the bar plot is usually more effective. They did research on how people perceive visualizations back in the 80s, I think, and they found that people are a lot better at comparing lines on the same scale than they are at comparing angles and areas. To see what I mean, try ranking these groups of animals in order from least to greatest. I'll give you a few seconds, but you might want to pause the video until after you're done. Now, here's a bar plot of the same data. Which of the two gives you a better comparison?